Welcome to class, everyone. Okay, today we're diving into a concept that literally underpins everything you're ever going to learn about force, motion, and energy. We're talking about units of measurement. Before we can build the house, we got to understand the bricks, right? So let's just jump right in. So picture this. You're standing on a train station platform, maybe running a little late. You look up at the digital arrival sign, and it's flashing this totally incomplete sentence. The train will arrive in 45. Well, 45 what? Minutes? Hours? Seconds? That single missing word completely changes your entire day, doesn't it? Now, take that exact same everyday problem, but imagine it happening in a physics lab, an engineering calculation, or, I don't know, a multi-million-dollar space mission. An undefined or just plain incorrect unit? That goes way beyond being mildly confusing. It's actually dangerous. Units are the agreed-upon standards we use to quantify the physical world around us. If you take away the unit, the number itself tells you absolutely nothing. All right, here's our quick roadmap for today's explainer. We're kicking off with the missing word problem. Then we'll hit the foundation of physical measurement. After that, derived units and prefixes, followed by some real-world physics examples. We'll wrap up with why units truly matter, and then a few quick practice questions. Section 1, the missing word problem, why numbers need units. Let's formally nail down what a unit actually is in physics. Okay, so here's the textbook definition. A unit of measurement is a definite, standardized magnitude of a physical quantity adopted by convention against which all other quantities of the same kind are compared. Right, sounds like a mouthful. But simply put, it's just your reference. Think about measuring a desk in your classroom. A single 1 centimeter segment is your reference length. So if that desk is 120 centimeters long, the number 120 is just telling you exactly how many times your 1 centimeter reference fits into the total length. Make sense? Moving right along to section 2, foundation of physical measurement, the core equation. Let's look at the incredibly simple math that makes all of this work. Check this out. Every single physical measurement follows this specific structure. Q equals N times U. That is, the physical quantity equals the numerical value multiplied by the unit. Notice the beautiful balance going on here. If you change your unit from meters to centimeters, your numerical value automatically shifts from 1 up to 100. But Q, the actual physical quantity, that remains perfectly balanced and totally unchanged. 1 meter is the exact same physical length as 100 centimeters. Same physical length, different unit, different number. Now, believe it or not, the entire framework of measurement across the whole universe is built on just 7 fundamental quantities. 7 base pillars that are defined independently. We've got length in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in Kelvin, amount of substance in moles, and luminous intensity in candelas. Before the International System of Units, or SI, was set up back in 1960, measuring things was just chaotic. A foot literally meant the length of whatever the local king's foot happened to be. The SI system finally ended all that chaos and gave global science one incredibly reliable standard. All right, section 3, derived units and prefixes, building blocks and scaling. So what happens when we need to measure more complex ideas than just those 7 base pillars? Well, we use derived quantities. These are basically just combinations of those fundamental ones we just talked about. Let's see how this builds using the concept of force. We start with Newton's second law, right? Force equals mass times acceleration. So if we take a 1 kilogram block and accelerate it at 1 meter per second squared, the fundamental units, kilograms and meters per second squared, combine, and together they create the derived unit of force, the Newton. So the unit of force isn't just some random arbitrary thing. It actually encodes the exact physics directly from the formula. But what about scaling? Physics deals with the incredibly massive and, of course, the impossibly tiny. So instead of making up completely new units every time we change scale, the SI system uses a brilliant set of prefixes. We just snap these prefixes onto our base units to scale all the way up to tera, which is 10 to the power of 12, or all the way down to pico, which is 10 to the power of negative 12. Let's look at how a physicist actually applies this across real scales, from the tiny nucleus of an atom all the way up to the solar system. If we're looking at something microscopic, a physicist might talk about a wavelength of 500 nanometers. That nano prefix simply means 500 times 10 to the negative 9 meters. It just handles all those annoying cumbersome zeros so cleanly and efficiently. Which brings us to section 4, real-world physics examples, units in action.
Time to take these concepts completely out of the textbook and see them working in real life.
Okay, so a massive point of confusion for beginners is the difference between mass and weight. When you step on a scale, you might have a mass of 60 kilograms. That is the actual amount of matter inside your body. But gravity is actively pulling on that mass. Following the formula W equals mg, multiplying that 60 by 9.8 gives a weight of 588 newtons. Weight is a gravitational force, and it's measured in newtons. Mass is the matter, measured in kilograms. They're related, sure, but they are absolutely not the same thing. Here's another really common everyday example. Say you're cruising in a car at 90 kilometers per hour. Kilometers per hour is a derived unit of speed. But remember, for doing physics calculations in dynamics, you always need SI base units. To actually use 90 kilometers per hour in a formula, we have to convert it by multiplying by 1,000 meters and dividing by 3,600 seconds, which gives us exactly 25 meters per second. The actual physics hasn't changed at all, but now we're finally speaking the right language for our equations. And what about your monthly utility bill? Have you ever noticed your bill for electricity in kilowatt hours? The SI unit of energy is actually the joule. But a joule is a really incredibly small amount of energy for everyday household use. So engineers adapted it. 1 kilowatt hour actually equals 3.6 million joules. The kilowatt hour isn't strictly an SI unit itself, but it's derived directly from them just to make practical daily use a whole lot easier for all of us. All right, moving into section 5, why units truly matter. We're going to talk about common mistakes and the strict rules we need to follow. Did you know that units are actually your built-in physics verification system? Think of them like an automatic spell checker for your math. If your units don't perfectly match on both sides of an equation, you've definitely made an error somewhere. And the rules for writing these units are incredibly strict. You can't just spell out 10 Newton as words or use weird custom mixed prefixes like 500 millimeters in standard equations. You absolutely must use the standard symbols, like a capital F equals 10N, and stick to proper base units and scientific notation. So here are the big common mistakes you've got to watch out for. Number 1, forgetting to convert your units first before you even start calculating. Number 2, dropping units mid-calculation and just sort of tacking them back on at the end. Don't do that. It completely destroys your ability to verify your work. Number 3, mixing up unit systems, like using grams in one spot and kilograms in another. Number 4, ignoring prefix scales. Remember, 1 millimeter definitely does not equal 1 meter. And finally, the absolute biggest mistake we see, thinking units are just some kind of optional decoration. Every single symbol in a formula, like V equals U plus AT, carries a unit. If they don't balance, the equation is wrong. Pure and simple. Okay, we made it to section 6. Quick physics practice questions. Let's simulate a really quick quiz just to test your comprehension of everything we've talked about today. Question number 1. What is the SI unit of force, and exactly how is it derived? Think back to that step-by-step derivation we did using Newton's second law a few minutes ago. Got your answer? All right, the SI unit of force is the Newton, represented by a capital N, and it's derived straight from Newton's second law, F equals ma, by perfectly combining the base fundamental units of kilograms and meters per second squared. Okay, our final and honestly most crucial question of the day. Can a number in physics actually be meaningful without a unit? Imagine seeing the number 500 sitting next to the word joules. Now take away the unit. Poof, we're just left with an isolated 500. Does that number actually mean anything to us anymore? The answer is rarely. With the exception of just a handful of very specific dimensionless quantities, a number without a unit is physically incomplete and scientifically completely meaningless. So let units be your guide, your verifier, and your absolute foundation. As we get ready to tackle super complex topics like quantum mechanics and astrophysics down the road, I want you to ask yourself this. If our entire understanding of the universe relies absolutely on the language of units, what happens when we discover something we don't yet have a unit to measure?